All right, so once we had that figured out, that there were discrete energies of these protons, discrete orbitals, we were able to explain these lines a little bit better. So when an electron in a hydrogen atom drops from a higher energy orbit to a lower energy orbit, so it's higher energy the further away it is from the nucleus. It takes more energy to keep that electron away from the nucleus because the electron is negatively charged, the proton is positively charged. They want to be closer together. So it takes more energy to keep it far away from the nucleus. So when we come closer to the nucleus, that means we're dropping from higher energy to lower energy. When we go down in energy, a photon is emitted. So it requires energy to go from here to here, but to go from here to here, we release energy. Oops. Absorb. So we need to absorb energy for the electron to get the energy to go to a higher energy orbital, and then it can release the energy when it drops back down to a lower energy orbital. And a photon with that energy and wavelength is emitted. So when, first specifically, when an electron drops from the n equals 4 orbit to the n equals 2 orbit, the photon that is produced from the hydrogen atom is this cyan colored line in the hydrogen atomic line spectrum. Okay, cool. So just to break that down a little bit more, if we're looking at energy increasing on the y-axis, then to go from an initial state that's lower in energy to a final state that's higher in energy, we need to absorb energy. So this photon of light is being absorbed by our electron so that the electron can go from this state to this state. Consequently, when we have a starting state that's higher than the final state, our electron is dropping in energy. It doesn't need to keep as much of its energy, so that energy is released as a photon. Okay, so energy is required to excite the electron from a lower energy orbit to a higher energy orbit, also called energy levels. So to get the energy required to excite the electron, it must be absorbed from the atmosphere. So typically absorbed as light or heat, different forms of energy. When the electron relaxes back to the lower energy level, it drops to a lower energy level, the electron doesn't need that energy anymore, so the energy is emitted or released, usually as a photon, as light. So using the Planck equation and the Bohr model, we can define the energy levels of the hydrogen atom and the spectral wavelengths we see in its emission spectra. So this is our Planck equation with Planck's constant, h. And this is a more expanded version of Bohr's model, where we're going from a final energy level to an initial energy level in energy to see what that energy change is. So the energy of the photon that is released, if you look at this figure, let's look at this red line, for example. So energy level 3 and energy level 2, or orbit 3 to orbit 2, results in this change in energy. So this change in energy corresponds to the energy of the photon that is released. So if we want to describe the line the wavelength of the photon that is released, then we have to talk about change in energy. When we're talking about the energy levels themselves, those are not changes in energy. Those are the energies of the electron in that orbit. But nothing is emitted or absorbed when the electron is in that orbit. It's just kind of hanging out. There's no radiation from that electron when it's in the orbit. Only when it goes between different energy levels do we get photons being released. Okay, so if we're talking about the electron, these are its energies. If we're talking about the photon that is emitted or absorbed when an electron changes energy levels, then we're talking about this change in energy, okay? It's a little complicated, but you just want to make sure you remember the difference. The energy of the electron is just an energy. So that's the equation that we had where it was just negative 2.179 times 10 to the negative 18th joules times 1 over n squared. That is just the energy of the electron. So I'll call that E electron. This energy, the energy change, is the energy of a photon. Okay, those are the differences. So let's do a practice problem. All right. What color of light is emitted when an electron drops from the n equals 3 energy level to the n equals 2 energy level? So we do not care what the energy at the energy level is for n equals 2 or n equals 3. We want the color of light that is emitted. So we want the energy of a photon. So that means we want this equation with the delta E. So that delta E, the energy that is emitted, is going to be equal to or related to the wavelength of the photon that is emitted. So I just related these two equations. So hc over lambda is going to be equal to this equation where the energy is in joules. So let's find out what color that is. Could be blue, could be green, yellow, red, but if you think back to the hydrogen atom emission spectra, green and yellow aren't on the emission spectra for hydrogen. So it's going to be blue or red. Let's find out which one it is. All right, so we've got our equation here. Hc over lambda is equal to negative 2.179 times 10 to the negative 18th. And we've got 1 over n final minus 1 over n initial. Let's plug in our numbers. So negative 2.179 times 10 to the negative 18th. And we're going from, the question was asking if we're going from 4 to 2. So 2 is our final. And 4 is our initial. So if we start at 4 and we drop down to 2, 2 is our final and 4 is our initial. It's a little confusing because 4 is bigger than 2, but it's just what the question told us. Okay, so let's see what that comes out to. Okay, so when I plug that in, I get negative 4.0856. I'll keep a few extra sig figs till I'm done with the problem. Times 10 to the negative 19th, and this is still in joules. Okay, so I'm going to drop this negative sign. So why can I drop that negative sign? Because the negative sign only tells us whether the light is emitted or absorbed. So we know from our question and from our initial and final states that to go from a higher energy level to a lower energy level, we are emitting our photon. So we don't need to worry about this anyway, but that is why it's still negative, because we're emitting a photon. So I'm just going to get rid of my negative sign. So hc over lambda is equal to that number. So I'll just call it E for now. But we want to get lambda by itself. We want to know the color or the wavelength of the light. So that's going to be, if we multiply both sides by wavelength and then divide by E on both sides. So HC over E, which is this guy now, is going to be equal to lambda. So let's see what we get. All right, so when I plug that into my calculator, I got that using this number as E, 6.626 times 10 to the negative 34th joules seconds as Planck's constant, and 3 times 10 to the negative, or 3 to the positive 8, sorry, 3 to the positive 8 meters per second at C. I get my wavelength to be equal to 4.865 times 10 to the negative 7th. And that's going to be in meters because C was in meters per second. So we had joule seconds times meters per second. I'm just going to use the units, not the numbers. I already told you the numbers. Divided by joules. So seconds canceled out in the Planck's constant and the speed of light, and joules canceled out in our energy and Planck's constant, so we end up with meters. So now we want to find out what it is in nanometers, because our visible light is given in nanometers. So we want 10 to the negative 9th meters in 1 nanometer. And when you plug that in, you're going to be adding, so you're going to be subtracting your exponents, which means you're adding 9 to minus 7. So we get 4.865 times 10 to the 2. So our 9 comes up and becomes positive, and we end up with times 10 to the 2 nanometers. So that's 486.5 times 10, no, sorry, 486.5 nanometers when we convert to standard notation. And that sorry, that for some reason corresponds to green, even though green is not in the spectrum for hydrogen. So let me check that out. All right, so I double checked my images here, and for some reason, so this image is not from your textbook. This image is actually from a Cengage textbook that I used last semester. So I apologize for the confusion, but for whatever reason, that previous textbook had the cyan line, which the cyan line from your textbook became green in their textbook, which is wrong. So let's go back to the one from your textbook. So the one from your textbook has these 4 lines: red, cyan, an indigo, and a purple. So the cyan is the one at 486.1 nanometers. And I got 486.5, which is pretty close. So I apologize for the confusion. But just like it shows here, this cyan line is the n equals 4 to n equals 2 transition. So my question, oh my goodness. I'm sorry. I really wanted it to be that cyan line, apparently. Let's just pretend the question was asking about n equals 4 to n equals 2, because I got that wrong. I'm sorry, guys. But I solved it correctly for when n, so for when it goes from 4 to 2. And we got 486.5 nanometers, which corresponds to the cyan line, like I said on this slide. I apologize. I'm sure this is going to be really confusing. I can remake this video if you need me to, but just ignore what I said before about the green line and ignore this image here where it has a green line instead of a cyan line. But just back on topic here, these lines of the hydrogen emission spectrum, the visible lines, are called the Balmer series, but there are also invisible lines that we can't see that correspond to the change in other energy levels. So the Balmer series is n equals 6 to n equals 2, n equals 5 to n equals 2, n equals 4 to n equals 2, and n equals 3 to n equals 2. So the purple line is 6 to 2. The indigo line is 5 to 2. The cyan line, which my image shows as green, is 4 to 2. And the red line is 3 to 2, which is the one that I was actually supposed to solve for in this problem. Sorry. So for 3, so when we go 3 to 2, it's going to be red. All right. But our other transitions, like from 6 to 3, or 5 to 3, or 4 to 3, those end up being in the infrared region, so that we can't see them, but they are, we can detect them, we can measure them. And when we go from 6, 5, 4, 3, 2 down to 1, those end up being in the ultraviolet region. So we can't see those either, but we can detect them. So the Lyman series is in the UV range, and it's always dropping down to the first energy level, the ground state. The Balmer series is always dropping down to the second energy level, and it's visible. And this one's called the Passion. I don't know if I'm saying that right, but the Passion series, and these are in the infrared region, and they're dropping down to the third energy level. Okay, cool. Let's stop here and go on to our next section.